Okay, so in the last lecture we were looking at methodology for counting of particles, and very quickly if we just repeat this methodology, that you put this kind of a counting frame which has a inclusion zone marked with green lines and an exclusion zone marked by the red line. So, any particle which touches the red line would be excluded from the count. Particles touching the green line will be included and particles inside the frame would be included. Based on this, we were able to separate out these three kinds of particles. So, there are 88 particles which are completely inside, 7 touching the green line and 14 of them touching the red line. Based on this, 14 we will not include in the count, we will just include 88 and 7, giving us a count of 95 in this frame, and then from that you can calculate number of particles per unit area. Now, this particular idea of a count on two-dimensional structure, which does not rely on what kind of shape of particles there are. Okay? Particle can be of any shape and you can still count them. This idea can be extended to the 3 dimensions, and then you can do a count and get the actual numerical density in V in a unit volume without knowing their mean tangent diameter, without knowing their shape. There can be particles of different shapes, you would be able to count those particles as well. This requires an introduction of a new kind of probe. Okay? So far the kind of probes we have been looking at are the plane probe, the line probe and the point probe. Now, we introduced this so called dissector, the 3-dimensional probe, okay, which would enable us to do a count in 3 dimensions, even though our materials typically are opaque and we are not able to see, we are not able to pass light through them. So, let us first look at how this, what is this dissector, the 3-dimensional probe. It consists of 2 parallel sections, 2 parallel plane probes. One we will refer to it as the observation plane and the other we will refer to as the lookup plane, and these two-dimensional sections are separated by a known distance h. Okay. So, I look at the microstructure on these 2 sectioned planes individually. Okay. Now, how can we do that? Well, if our materials are opaque, which typically they are, in your metallography sample preparation, you will first observe on one plane, then you will remove some of the material, okay, by polishing. Okay. By polishing, some of the material is removed, and there you basically you will get another plane on which you will again observe the microstructure. One of the planes we will call as the observation plane, other as a lookup plane. We can reverse them, it does not matter which one you call as the observation plane, which one you call as the lookup plane. The other thing is, we must also know the distance h between these 2 planes, which means in a sense we must know how much material we have removed after polishing. Now, amount of material that we will typically be removing will be very small, because if you are dealing with particles of just a few microns, you will remove only material of also couple of microns, not more than that. So, we must have some technique by which we should be able to estimate accurately how much material is removed, so that we get a distance between the 2 planes. We will look at the methodology later, how to get h. First, let us look at the methodology of the count. Both the planes have this counting frame that we have already looked at in the 2-dimensional count. So, exclude from the count the following particles in each of the planes. Particles which touch the exclusion zone, exclude them. Particles which touch both the observation plane and the lookup plane, you have to exclude. So, if I look at this figure here, this particular particle has a section in both the plane. The observation plane, the section is here, in the lookup plane, the section is here. This particle will be excluded from the count, while this particular particle has only a section in the observation plane. This particle is has a section only in the observation plane, which will be included in the count. So, in the end, which are the particles to be included in the count? Include in the count the particles which are found in the observation plane and not in the lookup plane, which means that this particular particle, which is whose section is in color, in white color, this will not be counted because this is in the lookup plane only and not in the observation plane. Once we get this count of only those particles which do not touch the exclusion zone in the observation plane and those particles which are only in the observation plane and do not show up in the lookup plane, that particular count, let that count be n. Then this is the effective number of particles present in the dissector volume. Okay. So, dissector, which consists of two parallel planes, the volume in between these two dissector planes is the volume of the dissector, which would be nothing but area of one of the sectioning plane, and that would be L square multiplied by h, and that is why you need h. So, volume of the dissector is L square h, and the numerical density, number per unit volume of the particles, is this total effective count n divided by L square h. In this particular methodology of counting, we do not need to know the shape, we do not need to know the mean tangent diameter, we are directly doing this count. And in fact, this method will enable us to obtain the mean tangent diameter, because now that I know NV, then it is a simple matter that we already know that NA equals h bar and V, and hence we would get the mean tangent diameter as NA upon NV. So, NV we get from the dissector, NA is the effective number of particles on a section, which also we can count. So, this method then is quite a powerful method, somewhat tedious of course, because you will have to do this count carefully on the two planes. You have to then exclude the particles as per the rules that I have already stated, and you have to do a very careful experimentation so that you get a very accurate value of the distance h between the two planes. Now, something more on the distance h. If we do not choose a proper spacing between the two dissector planes, then there can be counting error, and hence you will get erroneous value of the count. Now, let us consider two dissectors here. One is a dissector with some h value, and here it is a dissector with a larger h value. Now, in this particular case, the error can occur as a result that this blue colored particle that you are seeing is in between the two planes, but it does not intersect either of the planes. So, it will not show up in either of the planes, it will be missed from the count. Okay. So, this will be missed from the count, and hence you will get, and if you have large number of such particles, you can get large errors in your numerical density. So, general thumb rule you can take it as that dissector width should be kept around 1/4 to 1/3 of the average particle size. That should give you a reasonably good count. Now, let us look at how we can obtain the value of H. What could be a method of getting an accurate value of H? Anything you can think of? Take a FIB. Oh no, we don't want to go to very sophisticated techniques like FIB. Yes, you could, you should be able to get it. Yes, but we are not looking at very. We are not going into nanometers. If we are going to nanometers, then FIB could be a good idea. But otherwise, something very simple.
Average precipitate size must be known.
But that you don't know. That is what you want to find out. So, okay. So, here is a very simple way of finding H and very accurately as well. You are all aware of the micro hardness indenter, right? It is a pyramidal in shape. So, what you do is on the first plane, on the first section, you put an indent. It will have a certain dimension, diagonal length d1. When you remove the material, this diagonal length will go down, right? This much material is gone. So, your indenter should be long enough, of course. So, now on the second plane, you will see an indentation which is smaller and which can be measured as d2. Then simply the dissector thickness, because we know the geometry of this indenter, the Vickers indenter, if we take the Vickers indenter, then from the geometry this is the relation we get for H, the difference in the two diagonal lengths divided by approximately 7 here. That gives you H, and so this will give you a very accurate result. One of the things that you should be careful about is when you get the first section, do not put the indent immediately, first etch it, okay, because otherwise etching will ruin the geometry of the indent. So, with first etch, then put the indent, and you will put several indents, not one, and you will take an average value for H. Then after that, when you want to reveal the second section, you will polish it, polish some of the material off, then measure the indent before etching on the second section. That is what you have to be careful about, and that way you would be able to get H. Other thing that these indents are going to help you is, you want to observe the structure at the same in the same area. So, if you put your indents properly, you can locate your area after removing the material. So, indents will give you the dissector thickness, and it will also enable you to locate your area, because you have to go back to the same area and do the count. Now, here is one example that was taken. So, this is let us say is called the observation layer, this is the lookup layer. Now, as you can see, this was the basically the first layer that we took. So, this indents are sharp, this is that micro hardness indent. The second layer, which I have called it as the observation layer, the indents have become somewhat diffused here because of etching. So, before etching one would have measured it. So, here this diagonal length is 47 microns, for this the diagonal length is about 71 microns, and using this relationship we get spacing between the two sectioning planes as 3.45 micrometers, and this is done by measuring at least 7-8 indents, and an average value is obtained. Now, this is my observation layer. I have done some image processing to reveal only the contours of the graph nodules, and removed some of the other, so that counting is easy. Put the counting frame. Okay. So, this counting frame is put as before, and then do a count of this. So, the particles which are retained in the count are the yellow particles, and that number comes out to 95. And if you divide by the area, which is 624 into 340, you get a number per unit area is 4.47 into 10 to power minus 4 per micrometer square. Now, go to the lookup layer. We again just reveal the contours, put the counting frame, and again counted only the yellow particles. Now, it is a question that you have to now compare which are the common particles. So, here are actually the yellow particles which are retained in the count, but they are also common with the observation layer, and they are 83 in number. Okay. And we had a total of, in the observation layer, 95. That means, the difference would be the particles which are only in the observation layer and not in the lookup layer, and they have to be retained in the count. So, which I have now put them as green colored particles in the observation layer. Okay. So, these are the particles which are retained in the count. The yellow ones here are excluded from the count because they are appearing in both the observation layer and the lookup layer. So, there are only 12 particles, 12 such particles which are only in the observation layer and not in the lookup layer. This number 12 you divide by the volume of the dissector. So, the area of the dissector plane you know, multiplied by h, which we had calculated as what, which was 3.45 microns. So, one would multiply it by 3.45 microns to get this as the volume of the dissector, and this gives me a number density of 1.63 into 10 to power minus 5 per micrometer cube. So, now I have really got the actual numerical density of the graphite nodules. I can get the mean tangent diameter as Na upon Nv, and that turns out to be 27.4 microns. Now, you can also just flip the layers. What you called as the observation layer, you can call it as the lookup layer, and what you called as the lookup layer, you can call it as the observation layer, and do a count again. So, you will get from the same dissector, you will be able to get 2 counts, and you can take an average of that. Now, I just want to give you that if our shape assumptions are okay, then what kind of a count what kind of a numerical density I would have got for the same material based on only a single section count. Then remember from the last lecture that numerical density can be given by this relationship, where beta is a shape measure, Na is the number per unit area on a section, and V sub V is the volume fraction. So, assuming spherical particles, near about spherical particles. So, then we can take this shape measure beta as 1.382 from the last lecture. Na I just now mentioned on that, but one section was this much, 4.47 10 to the power minus 4. Volume fraction of these particles were measured using point count, that gave me 0.17, and calculating from this, it gave me a numerical density of 1.66 into 10 to the power minus 5 per micrometer cube. and the dissector method gave me a density which is very close to this density, as you can see. So, perhaps our assumption of spherical shape is okay. If our assumption was wrong, then these two values could be very different. Okay. So, this kind of concludes some of the basic stereology related to single section plus an introduction to the dissector. But so far what we have assumed is that our materials are isotropic, which means that whatever features we are looking at, they are randomly oriented, they are randomly distributed. Now, you can have microstructures which are not randomly oriented, or they have some kind of an orientation. And a good an extreme example could be if I had a fiber composite material and all fibers are in the same direction, then that is an example of a highly oriented structure. Somewhat less oriented structure could be I roll a material, grains become elongated in the rolling direction. Then again, not all directions of the grain boundaries are have the same uniform orientation. Okay, there is a preferred orientation in the rolling direction. Then some of these methods will not work directly. You have to modify their working. You have to be careful with such microstructures, and that is what we are going to see now.